So in this application, you can observe a normal flat plate collector is connected to the power plant. So from the flat plate collector, we are going to increase the temperature maximum up to 100 degrees centigrade. So within 100 degrees centigrade, whichever the fluid is able to evaporate, or it can create high pressure vapors, such liquids or the material can be used in the flat plate collector as a fluid, working fluid. So for example, here they are using the water as a fluid which can vaporize at 100 degrees centigrade, and at very low temperatures, whatever the water is heated up to 70 to 100 degrees centigrade, so that is exchanged with this working fluid in the power plant. So that working fluid they have given example as butane. Okay, so that butane can vaporize in very less temperatures compared to the water temperatures, or below 100 degrees centigrade. So once these butane vapors are created, so those can be supplied to the turbine, which can work with butane vapors, and the power from the turbine can be connected to the generator or pump or any rotatory machines for our applications. One of the application here is shown as pump. So by notation, they have shown to lift the water from the well or somewhere. They have shown one notation here. And this rotatory machine can lift water, or it can operate some machines or something, or it can also connect to the generator to convert that thermal energy into electrical energy. And water is lifted here by the pump. It is supplied to the irrigation purpose. And butane vapors, once they are converted, that all pressure energy into rotatory motion in turbine, so that partial liquid and vapor stage of butane, that will come to the condenser here at the bottom. And in the condenser, we are again using the same water from the pump or external water for cooling, so that butane vapors are converted into liquid, and this liquid butane can be pumped to the boiler or the heat exchanger again. So like this power plant cycle will work continuously. Similarly, for heat exchange, we can either go for the heat storage device or the direct heat exchangers, where we are going to extract the heat from the water to the working fluid, that is butane. So here, as flat plate collector is shown, this example is for the low temperature solar power plant, which is below 100 degrees centigrade. The next is medium temperature. You can just see. So medium means we have to go for just above 100 degrees centigrade. So for that, one can go for the concentrating type of collectors. So that concentrating type of collectors are, earlier we discussed about parabolic type, cylindrical type, or spherical or hemispherical type of mirrors. So by using such focusing collectors or the concentrating type of collectors, as shown in this sketch, we are using cylindrical parabolic collectors. So directly the solar energy is focused at a given line focusing devices or the point focusing devices, where the temperature is going beyond 100 degrees centigrade. And there, to extract that heat, water may be directly converted into steam, and directly you can run the turbines, or else to extract more heat or more vaporizing temperatures at very high temperatures, then we can go for the different oils also, which can vaporize at a very high temperatures. So in this example, they have shown oil is passing through these all focusing collectors, and it is coming to the heat exchangers here. So there are number of heat exchangers, 1, 2, 3. So in third stage, you can see the complete vaporization of the working fluid is there. So for that, they have used water in the second cycle. First cycle is completely circulating in the given solar collectors. So as the high temperature working fluid like oil comes to the third heat exchanger, it will vaporize the water and it will be circulated to the high pressure turbine here. So turbines here, two stages have shown, because temperature is very high. In again number of stages, we can convert that energy into mechanical work. So you can go for high temperature, sorry, high pressure or high medium pressure or the low pressure turbines. Like this number of stages can be connected, and these turbines are connected to generator here. The sixth point is generator. This will directly convert the thermal into or mechanical into electrical energy. So thermal energy is converted to mechanical by turbines. Then generator will convert mechanical power to or rotation into electrical energy. Then once this steam is taken here from the generator, before that, whatever the water after condensing from the turbine, at the outlet of the turbine, you can see a condenser or the cooling tower. So in big power plants, if you see the coal thermal power plants, we will be having a cooling towers. So what it will do is, whatever the hot water is coming from the turbines at low pressure or the high pressures, that will be taken to the cooling tower and it will be sprayed from the top. And whatever the cool air is passing from the bottom to top, it will convert that hot water into cold water. And this liquid water can be pumped to the condenser or the collector, and again it can be pumped to the heat exchangers. So once this water in low temperatures or the low pressure is coming back to the first heat exchanger, so slowly in number of stages, first, second, third, like this, the heat of the water can be increased, and at third stage and fourth stage, if you see like a superheater or the reheater, one more, like 4 heat exchangers they are using. At fourth stage, if you see, the heat extracted by the water from the oil loop may be very high. So like that, depending upon the different temperatures. Here, third stage heat exchanger is given to the high pressure turbine, and fourth stage, if you see, it is given to the low pressure turbines. So like this, we can utilize all these heat exchanging devices and the steam of water in different stages. Like that, we can convert the thermal energy into mechanical energy. Any doubts here? Any doubts in low pressure and medium pressure applications? Any reply? Okay, next we'll take the high temperature applications. So in this application, if you see, at a given tower or a high point, we are going to fix a collector or a receiver, central receiver. And at the given point from the top of the tower, we are going to focus all the solar radiations by mirrors or focusing collectors or the concentrating collectors to the center of that receiver. Then we are going to maximize the absorbed temperature, maybe up to 350 degrees centigrade or up to 400 degrees centigrade. So once this temperature is achieved, then we can run the same power plant cycle like using turbine, condenser and pump to get the electrical energy. Okay, so either you can draw the diagram which is shown in the right side or in the left side by line diagram. And application you can see here. So there is a big tower here, and at the top you can see this is like a steam generator. Okay, so either you can go for the oil or some water. You can get the superheated water directly from this type of applications where all these solar reflectors are going to focus the radiations to the top of this receiver. And once that is done, the superheater steam can be passed to the turbines and generators which are connected at the bottom side. And this will be connected to grid. Yes, one of you can reply me what is happening. All of you understood the three types of applications of solar energy. Is there any difficulty in connectivity? Any network issues are there? Any reply? Okay. So this is the one of the application what I have showing here for the high temperature applications where all these reflectors connected at the ground here are going to focus all the incident radiations to the top of this tower where the receiver is kept, and in this receiver we are going to absorb all the heat and we are going to convert that into superheated steam, and that can be utilized to run the turbines and generator which are connected in the on the ground, and from this we are going to transfer the electrical power to the grid, and that can be supplied to the cities. Okay, next one is, so as I told, directly you can convert all the heat and absorb to the working liquids or the working fluids for running the turbine or for the heat exchangers. Apart from that, you can go for the heat storage also. Like as I told earlier, latent heat storage materials or the sensible heat storage materials like rocks or pebbles or some phase change materials also that you can utilize. And from this thermal storage here, see, this is the thermal storage device like a heat exchanger. So whenever the power or the electrical power conversion is not required, until that you can store all the heat from the solar energy. It may be running with high temperature or the medium temperature. So in between these two lines, you can show a flat plate collector or a concentrating collector or a tower type collector for high temperature, whatever. And whatever the heat is collected, that will be stored in the heat exchanger or the thermal storage device. And later, when in the remote places or in any given time, only that time, if the power is required, then only I will extract the heat and I will run this uh, turbine and the generator. So like that, you can also use some heat storage devices. Yes, how much? 21 have joined. Okay. Now it is connected.
Yes, sir.
Is the audio and video is reaching to you? Okay. Yes, thank you. So again, coming back to the next slides. So next we'll see the application of solar energy for distillation purpose. So any island if you take where seawater is plenty, seawater is available, but we cannot get the drinking water properly. And even some villages or the places if you see where the transportation of the water is not possible, or we cannot have the pure drinking water. In such cases, we can have the remote water distillation plant or the water purification plant. In that, you can see this chamber here. There's a construction like a water container. A big tank will be constructed with insulating materials. And one side you can fill the impure water through the filler here. On the left side, we can have the outlet. So outlet should maintain the proper level in this container. And the complete wall and the bottom side of the container will be having black surface or the black painted surface so that it can absorb maximum temperature or the heat. And at the top, we'll be having transparent covers which can collect all these vapors of the water once it is started with the solar radiation. So solar radiation can be passed through these transparent covers. So inside this black surface will absorb the maximum heat, and from that black surface the water temperature can be increased and part of the water can be vaporized. So once the vaporization starts, these inclined surfaces, what you can see at the top, can collect the droplets of the water, and due to this inclination, the droplets will be collected at a given points and it will be passing through up to chambers or the channels at the side. So at the side, if you see, these are the two channels through which we are going to collect the pure water. Okay, so all the impurities will be restored back in the container in the distillation plant. Only the pure form of water in the vapor state will be collected on the transparent covers or the upper cover, and those droplets, because of this inclination, will be collected at the side channels. So simple application, but one should know the how it can be utilized. So this is called the distillation plant, and this application you can just observe in remote places where pure water is not available, or in places where the sea water is plenty but we cannot have the pure drinking water. Is that understood to everyone? Connectivity, any issue? Okay, thank you, Vivek. Next one you can see in the self-study topic itself. Other thermal application is to extract maximum temperature. Okay, so that is example, you can take a furnace. So in the furnace, if you see, earlier days we had a fuel combusting furnaces where maximum pollution was happening. Next we had electrical furnaces nowadays, which are consuming maximum electrical energy and very high voltage is required, and also maintenance of that devices and the cost of that device is very high. So in such situation, one can think of this solar furnace. So here also what we are doing is the target specimen where we are going to keep the metal which is to be melted. So one position can be made here like a tower. On that tower we can fix this specimen which has to be melted or which has to be converted from solid to liquid state. So up to that temperature, we need the heat. For such applications, what they have done is they are going to fix the number of heliostats or the mirrors or the focusing plates on the ground in different angles like this. And these all mirrors or the heliostats should be focusing the given solar radiations to the concentrator here. And this concentrator, which may be in the cylindrical or the spherical form, is insulated at the backside so that maximum heat should not lose. Okay, so maximum insulation is possible so that it is insulated at the backside. And from this concentrator, what will happen? It will be focusing towards the focal point of this concentrator. So this is a simple device which is using only the light energy just to convert that light energy or the focus of that light into different directions. That is done. And all these radiations are focusing on the given point of the specimen. And the temperature at this point is reaching around 3000 to 3500 degrees centigrade. The application, if you see, can you see all of you this example? Yes. See, one of the example I have taken here to explain the solar furnace application. So this is constructed in Odilo in France. So this building is constructed for solar furnace application. The parabolic shape of the mirrors you can observe here. So all these solar radiations are focused to the parabolic shape of concentrators. This will focus all these radiations towards the center of the building. And there may be one window is prepared, and through that window all the energy is supplied, and one given point or the receiver point, it will be having the target specimen. That specimen which we want to melt it at very high temperatures. Or one more sketch I have taken here. That here you can see clearly. The design is like this. At the top you can see number of mirrors are kept on the ground in different positions. Okay, and all are focusing towards the concentrator, which is in parabolic shape. And these radiations which are coming parallelly are focused to the one given point or the target. See here, actual picture is below. See these heliostats which are placed on the ground. All these heliostats or the mirrors will focus the solar radiations towards one point or one uh, spherical or the parabolical concentrator. On this it will be focused, and this parabolic shape will be having one focal point. Exactly at that focal point inside this building, the specimen chamber is prepared, and in that specimen will be kept. Okay, so like this we can achieve maximum temperature. So it is going beyond 3500 degrees centigrade, which is required for many metals which can be melted easily by using just natural energy. So for this, provided we should have area, big area, and all these technologies and proper focusing points and components. So one can achieve this solar furnace application also. Okay. Anything you want to discuss in these applications? Shall you continue? Okay. So next, coming to the other part. So until now we discussed the self-study topics. So just I'll show the syllabus here. What is left in the syllabus we'll see. So in the second chapter, we discussed about self-study topic, that is application of solar energy for power, heating, cooling, distillation, solar storage or other applications that we discussed. Earlier we discussed about the effect of various parameters on the collector performance, that is selective surface, orientation, fluid inlet temperature, number of cover, dust, etc. Now we need to discuss the performance of liquid flat bed collector by different correlations, and later we'll discuss the PV conversions. So in this performance analysis of liquid flat bed collector, if you see, earlier we saw the energy balance equation and how the flat bed collector is designed. What is the meaning of stagnation temperature? Now from today we'll discuss what do we mean by transmissivity of the cover system, transmittivity and absorptivity product, some simple numerical examples of that. Then later we have overall loss. So loss from flat plate collector from the top, then bottom, side loss. Okay, all these coefficients, all correlations should be provided. So derivation is not given here. We need to again depend on the equations. Only equations you have to recall. Temperature distribution in the flat plate collector, then heat removal and collector efficiency. So these all things we need to discuss in this remaining part. Okay. So coming back to our PPT. So to understand what is transmittivity of the cover system, if you see, so in the physics, if you just recall the things in optical physics, what you have understood is whenever the light passes through a transparent cover, the directions of the light is going to vary. So in the sketch, you can see on the right side, the incident beam radiation from the solar light, whatever the beam radiation is coming, that is denoted by IBM, that is falling on the cover plate here. So this is medium 2. Medium 1 is here. So once this is falling, so always in optics we know there will be reflection from the given surfaces, little bit reflections, and some part of the energy is absorbed and also some part of the energy is refracted. So like this different uh, passage of light will be there. And with respect to light, if you study, we are going to study about only incident ray, reflected and refracted beam. But for the radiation, if you see as the energy part, if you see in the light, then we have the absorption. So here refracted beam and reflection beam are denoted by tau r and tau alpha, tau r and one more term is there. So tau r1 and tau r2, like that. Reflected beam radiations, that is tau r, where the beam radiations or the light reflections or the refractions are there, that is denoted by the tau r, which is because of the transmissivity of the cover plate. One more term is there, which is the absorptivity, that is tau alpha. So in the left sketch, you can see again one glass cover is taken. The beam of light with radiation or the energy like heat is passing through the glass cover. While passing through the glass cover, it is going to have some refraction where theta 2 will be there. Means there will be change in the angle from incident to refracted beams. But for the incident to reflected radiation, there is no change in angle. This is the law given by Snell's law. That is one case. And once this energy passing through the plate, see at the bottom you can see we have the selective coated absorber surface with some absorptivity alpha. Okay, and how this energy available on the absorber plate, if you observe, see the solar flux incident on the absorber plate will be after transmission from the glass cover. So there will be some loss. So that loss we are going to denote it by tau r, that is nothing but the transmittivity due to reflection refraction from the glass cover, and after which it is going to reach the absorber plate here at the bottom. Solar flux absorbed by the absorber surface, that is given by total radiation into tau r, or the tau is nothing but the transmittivity, how much it is transmitted through the glass cover on the transparent cover, that is because of reflection refraction, and transmittivity due to absorption. So that absorption is what is denoted by alpha here. So once you multiply these two terms, there will be some reduction in the total solar flux. So say for example tau into alpha, if you multiply, it may be 0.8. So 0.8 means 80%. If you multiply with total solar radiation, 20% is the loss which is available on the flat plate absorber, which is passing through one of the glass cover. Like this, if you increase number of glass covers, losses is going to increase. So those losses are due to, one is absorption, one is by reflection and refraction. Okay, now you can see after reflection from the, or whatever energy emitting from the absorbed plate, if you see, that is the heat lost by the absorber plate, that can be given as IT1 minus T here. IT is nothing but total radiation from the solar energy what is coming. Now tau, if you see, tau is what? The reflected radiation loss. Why? Because it is coming from the absorber plate and it is having some losses. So that we are taking 100 minus that loss, how much is retained in the reflection, and absorptivity means after absorbing from the plate, how much it is available, that we are going to multiply. So finally, how much it is reflected will be very less compared to the total radiation coming from the sun. So I think the theory behind these sketches, all of you understood. So once if you recall the physics behind this, one can understand why there is a loss because of the transmittivity and absorptivity. So I think all of you can remember the Snell's law. Yes. There's no reply. Okay. So from the Snell's law, if you recall the law, what it states is the angle of incidence and the angle of reflection both will be having in the same medium with same angles, that is theta 1, and refracted beam will be having some deflection, that is theta 2, what is shown in the medium 2. So by which one can write that is n1 sin theta 1 equal to n2 sin theta 2, or else you can take the ratios and you can write sin theta 1 by theta 2, that is angle made by reflected beam or the incident beam to the sine of refracted beam, that is theta 2. That can be written as N2 by N1. So N2, N1 here are the reflective indices of the materials. Okay, so that refractive indexes of the two medium can be shown as N1 and N2. So N1 is for air here, N2 is for glass or the transparent cover. And reflectivity, as we studied in the solar radiations geometry and measurement earlier, in this flat plate collector also, the reflectivity can be given as the reflected radiation to the beam radiation. So as you can see at the top, the reflectivity. Reflectivity means the ray of light is reflecting back to the same medium in the same angle. So how much it is reflecting to the total radiation applied on that surface. That ratio, if you take, that is giving the reflectivity of the given surface. So that is denoted by again rho. So rho in entire subject, if you see, it is a reflectivity of the given rays. Then coming back to the absorptivity of transparent cover, that can be denoted by tau alpha. So how much it is absorbed or what is the loss, to find out, there we can take the ratio of incident radiation to the total radiations or the radiations incident on the absorber. Okay, so tau alpha, if I speak, you have to focus on the absorber, not on the glass cover, because after passing through the glass cover only the absorption will happen. So once the solar radiations pass through any medium, some absorption will be there. So that radiations after absorption, if you see, that I can call it as IL after the losses due to absorption from glass cover, that I will take IL, incident radiation on the absorber plate after the losses, to the total radiations available outside the glass cover, that is IBN. And by some researchers it is also shown as tau alpha can be written as, for the tilted surfaces, as E equal to K delta C by cos theta 2. So here K is constant of proportionality. So that value is around, yeah, that constant is depending upon the different materials. That is constant of proportionality given by extinction coefficient. And here delta C is the thickness, okay, the thickness of the transparent cover. So that is delta C. So delta C indicates thickness of the cover plate divided by cos theta 2. So here theta 2 is the angle of refraction. So angle of refraction depends on angle of incidence also, because if you incident the radiation exactly at zero angle without any making any angles, then it will be maximum, because cos of 0, if you see cos theta 2, if it is 0, then maximum radiations with less absorption is possible. As the inflation of solar radiations go on increasing, the absorption rate also increases. Okay, so I think time is 3:16. We'll stop the class today. Next class again recall back all these equations and we'll go to the next topics. Okay, any difficulty in the network?
No, sir.
Many are not replying.
No, sir.
No,
Your
sir.
audio is not audible to me. Just a minute. Now you reply.
Yes, sir.
Now speaker is on. Okay, just a minute. See, throughout the class audio was clear, no?
Yes, sir. It was clear, sir.
Yes, sir.
Okay. So stop here. We'll continue the next class. Okay.
Okay, sir. Thank you, sir.
Yes. Thank you.